Thank you for visiting my poster. My name is Hyeon-Jin. Today, I will introduce our work, Streamlined Knowledge Distillation. Before explaining our method, let me first introduce the background. Knowledge distillation aims to train a compact student model by transferring knowledge from a large teacher model. There are two types of knowledge distillation, feature-based KD and logic-based KD. Feature-based KD align intermediate feature representations between the teacher and the student. This can provide rich knowledge and often lead to high performance. However, it also has some practical limitations. It requires high computational cost, and when the teacher and student have different architectures, extra projection models are often needed. On the other hand, logic-based KD directly mimics the output predictions of the teacher. Because it only uses output logic, it is simple, scalable, and easy to deploy. However, its performance historically have been lower than feature-based method. Therefore, recent loss-based KD methods have tried to close the performance gap with feature-based KD, while keeping the scalability and simplicity of logic-level supervision. To achieve this, recent methods have introduced the multi-knowledge alignment and relational structure modeling. However, these approaches still have three key limitations. First, redundant objective. Second, suboptimal transformation. Third, ill-suited loss functions. Motivated by these limitations, we proposed SKD. The main idea is simple. Instead of using many objectives, SKD transfer only two essential forms of knowledge. The first one is instance-wise semantics. This captures interclass similarity and fine-grained information for each sample. The second one is direction-wise relational structure. This captures pairwise directional relationships and output correlation across samples. Now let me explain each part of the proposed method. First, for instance-wise knowledge, SKD follows the original KD formulation. It aligns the teacher and student subfund probability distribution, and this is formulated as a KI divergence loss. Next, for direction-wise knowledge, we build a Gramian matrix from the output logic. This allows us to capture pairwise directional relationships between samples. The process is as follows. First, we apply Euclidean batch normalization to the output logic. This normalizes each logic vector and removes scale information. As a result, we can focus on pure directional information. Then, we construct the Gramian matrix using the normalized logic. Each entry of the Gramian matrix represents the cosine similarity between a pair of samples. After that, we compute the difference between the student Gramian matrix and the teacher's Gramian matrix. This difference shows how much the student's relational structure differs from the teacher's relational structure. Then we estimate the empirical batch covariance from this difference matrix. Using this covariance, we define a direction-wise loss based on the Mahalanobis distance. Unlike the L2 norm, this Mahalanobis-based loss considers variance and correlation across relational difference. However, there are some practical issues. The covariance matrix may not be positive definite. Some matrix inversion can be unstable. Also, directly computing the inversion can be expensive because it has cubic complexity. To solve this problem, we use two stabilization techniques. First, we use Tikhonov regularization. Second, we use Cholesky decomposition. An important point is that our direction-wise loss can be interpreted as a whitened L2 norm. By decomposing the regularized covariance matrix using Cholesky decomposition, we can rewrite the Mahalanobis loss as an L2 norm in a covariance whitened space. This means that our loss is still simple like L2 norm, but it is aware of variance and correlation. Now, let me move to the experimental research. In the quantitative research, SKD shows strong performance on Cypher 100 and ImageNet. It consistently outperformed prior loss-based KD method. This shows that our streamlined two-knowledge design can achieve strong accuracy and scalability. We also evaluate SKD with qualitative research. Qualitative research shows that SKD produces better gradcam++ attention, more closely matches the teacher's Gramian matrix, and requires the shortest per batch training time. This confirms that SKD is both effective and efficient. To summarize, SKD is a simple and effective logic-based distillation method. It transfers only two essential forms of knowledge, instance-wise semantics and direction-wise relational structure. With this streamlined design, SKD achieved strong performance, better relational matching, and high training efficiency. Thank you for listening to my presentation.